In this video, we are going to extend our understanding of stoichiometry by combining the molar ratio with many of the pathways into and out of moles that you have learned throughout the course. This diagram is called a mole map. The mole map helps you decide which conversion factors you need in order to get into moles and which conversion factors you need to get out of moles. At the very center of the mole map is the molar ratio from the balanced chemical equation. The molar ratio is simply the relationship between the stoichiometric coefficients that we discussed in the previous video. Throughout this course, you have learned several ways to convert into moles. If you start with a mass of a solid, you can use the molar mass in order to convert from grams into moles. If you start with the volume of a solution, then you can use the molarity of that solution to convert from liters into moles. And if you have the volume of a gas that is not at STP, you can use the ideal gas law, since the variable n in the equation PV equals nRT represents moles. These same conversion factors can be used in reverse to convert out of moles. We also learned about Avogadro's number, which relates moles to particles. Keep in mind that since a mole is simply a very large count of particles, we can apply the molar ratio directly to particles, just like we can moles. Finally, if a gas at STP, we can use the molar volume of a gas, which tells us that 1 mole of any gas occupies 22.4 liters at STP. Likewise, the coefficients in a balanced chemical equation can relate volumes of gases directly, provided that all of the gases are measured at the same temperature and pressure. At first glance, the mole map may look very overwhelming. However, stoichiometry really is as simple as 3 steps. Step 1, get into moles if you are not already in moles. Step 2, change substances. For that, you will always use the molar ratio from the balanced chemical equation. And finally, step 3, get out of moles, if necessary. If you remember these 3 steps, most stoichiometry problems follow the same process. Let's begin with a mass-to-mass stoichiometry example. Since we are converting from the mass of one substance to the mass of another substance, our solution pathway will look like mass to moles to moles to mass. We first use the molar mass of the starting substance to convert into moles of that substance. Next, we use the molar ratio from the balanced chemical equation to change from moles of one substance into moles of the other substance. Finally, we use the molar mass of the second substance to convert back into grams. How many grams of SO2 will form if 200 grams of O2 completely reacts according to the equation below, assuming excess H2S? The phrase excess H2S tells us that there is more than enough hydrogen sulfide available. Some H2S will remain after the reaction is complete, so we do not need to base our calculations on it. Instead, we base our calculations on the 200 grams of O2, since oxygen is the reactant that limits the amount of product formed. I find it helpful to identify the substances involved in the calculation directly on the balanced chemical equation. Here I have circled O2 since it is the given substance, and SO2 because it is the substance I'm trying to find. I simply crossed out the H2S and the H2O because they are not needed for this calculation. This makes the equation feel much easier to focus on. I begin with the 200 grams of O2. First, I use the molar mass of O2 to convert from grams of oxygen into moles of oxygen. Next comes the stoichiometry step. Using the balanced equation, the molar ratio is 2 moles of SO2 for every 3 moles of O2. Finally, I convert from moles of SO2 into grams of SO2 using its molar mass. Notice that every conversion factor is arranged so that the previous unit cancels. A good habit is to copy both the unit and the chemical formula from the numerator of the previous conversion factor into the denominator of the next one. This helps prevent common mistakes. After performing the calculation and rounding to 3 significant figures, we obtain 267 grams of SO2. Since oxygen was the reactant that limited the reaction, we can say that 200 grams of O2 is the limiting reactant and 267 grams of SO2 is the theoretical yield of sulfur dioxide. How many grams of H2S are needed to react with 200 grams of O2? Once again, I begin by identifying the two substances involved. I can circle O2 since that is the given substance, and H2S since that is the substance I need to calculate. I can cross out the remaining substances because they are not needed for this calculation. The molar masses are provided underneath the balanced chemical equation. First, I can use the molar mass of O2 to convert from grams into moles of O2. Next, I use the molar ratio from the balanced chemical equation. 2 moles of H2S for every 3 moles of O2. Finally, I use the molar mass of H2S to convert from moles of H2S into grams of H2S. After completing this calculation, we find that 142 grams of H2S are required. The correct answer is choice C.